Welcome to CodeUp. This is the third session of CodeUp that we are having right now. Today we are going to talk about artificial intelligence and deep learning. So CodeUp is a series of talks by developers. It's organized by Citrus Payments. Citrus began 5 years back as a startup, and it has built a lot of developer-friendly APIs, which a lot of developers code on. A lot of developers, thousands of developers actually recommend their clients to us. And whenever there's a requirement for a payment solution provider to come in, a lot of these developers come and refer their clients to us. Citrus is used successfully by over 22 million consumers, and we process approximately $3 billion in transactions annually. On a day-to-day basis, we interact with a lot of developers, and in the process, we came across some very innovative ideas that is changing the way the world communicates. And we wanted to create a platform per se where all these developers would come together, interact, learn a little bit about how things go, what cool things are coming into the market. And it is with this in mind that we started CodeUp. The previous sessions of CodeUp saw companies like Twitter and Truecaller come and demonstrate their developer tools to the developers. In this session, we are focusing, as I said, on artificial intelligence and deep learning. We have developers from 3 interesting startups working in this space. We have Keshav from Niki.ai, who will be speaking about techniques in NLP and search. We have Chandrakant from Arya.ai. Chandrakant would be speaking about deep learning for computer vision. And we have Vivek from Snapshopper. He'll be sharing his views around the topic, is deeper the better. After the three presenters have presented their topics each, we shall have a joint Q&A where we'll have all 3 speakers in front, and we could have an open panel kind of a discussion. Right, so I request Keshav to get started.
So I would actually be talking about various steps in natural language processing and what it basically entails. We at Niki.ai are developing a chatbot to that you can converse with to basically carry out any kind of transaction-oriented goal. Like you want to book a cab, you want to buy something, you are looking to get an outstation cab, you are looking to travel, let's say, from here to Hyderabad by booking a bus or a flight ticket. So anything that involves a transaction, a payment to book a service or buy something, we are building a conversational engine for that, so that you can go over to that space, chat in a natural human manner with a chatbot, and it will understand what you have to say and come back with appropriate responses and recommendations, take the payment, and then confirm your booking. So the core part of what we do in terms of technology is going to be natural language processing. So I'll talk about this. It's going to be rather bit theoretical in nature, but bear with me, it should be, I hope you guys find it good. So natural language processing as such is a subfield of human-computer interaction. Up till now, the human-computer interaction that has been there has been with the trackpads and the mouses, right, which is rather mechanical in nature. The kind of interaction that we envisage in the future is when humans wouldn't have to adapt to the computer way, but computers should adapt to the human way of interaction, be it gesture-based or be it touch and tactile based or be it language based. So computers should actually be adapting to the ways that humans interact. Natural language processing is it's a subfield of human-computer interaction where a computer basically converses with you for anything, like for a definite goal or for just a chit chat or for something else. There are 2 parts to it. One is the natural language understanding, in the sense that when you say something, a user input, could be a sentence, could be a phrase, could be a bunch of sentences, to make sense out of it, to make a complete meaning out of it, just as a human does. That part is called natural language understanding, and once a computer has understood the meaning, the semantic content of a sentence, responding appropriately based on that sentence and the previous context of the conversation that has been built up so far is called natural language generation. So primarily I'll be talking about natural language understanding. It is the most researched part as such as of now. Natural language generation is still, I would say, in its infancy, in the sense how to maintain a coherent conversation over, let's say, 20 or 30 different steps and utterances is something that is still under research. So moving on. So there are like various steps in natural language understanding, and I'll be mostly talking about these steps in detail. There are three main steps in natural language understanding. The first is when you receive a user input, you normalize it. By normalization, I mean you transform that input in a way that forms a suitable input for rest of the machine learning systems for natural language understanding. So normalization basically has these four steps typically that we do. One is the spell check thing, like if a word has been misspelled, you actually spell correct it. Not sure if you are able to see the examples, but the first example is for spell check, my operator is AXL. So somebody has mistyped ASL and mistyped replace C with an X. So it will be able to spell correct that. That is like the basic part of normalization. The second is abbreviation expansion, in the sense, let's say somebody says the UN is scheduled to meet today. So this basically means the United Nations is scheduled to meet today. Now abbreviation expansion becomes tricky when you have alternate expansions for the same abbreviation. Like WWF could either mean the wrestling wala thing, or it could mean World Wildlife Fund. So it becomes tricky in that manner. The third is colloquial terms, in the sense somebody writes what you're doing. Watcha basically means what are you, and doing is doing. So the expansion of colloquial terms also is very context sensitive. And the fourth is special nouns. Special nouns are basically, names of the places or names of the bands, which are rather tricky to deal with in certain scenarios. Like the Who is a band, but if somebody says the Who is my favorite band, you would also end up interpreting it as a question, who is my favorite band? But actually the in front of Who characterizes it as a special noun, which means name of a band. So it becomes very important as a first step in natural language understanding to have appropriate algorithms for each four of these: the spell check, the abbreviation expansion, the colloquial terms, and the special nouns. Once you have done the normalization part, the most crucial step that you do after you get a user sentence is part of speech tagging. Part of speech tagging, at least in the written form. So like we have a chatbot that you can actually converse with on an application, right? So you actually type the sentence and terminate it with a full stop. So the sentence boundaries are very clear, but if you go into speech recognition part, in the sense that if the same chatbot converses you over voice rather than text, the sentence boundary disambiguation also becomes very important, but we are not going into that. So once you have gotten a complete sentence, its part of speech tagging is very important, because this will form basis or the input for rest of the things out of which you extract meaning. Interestingly, until 1980s or 1985 almost, nobody took this seriously, in the sense that there were people who had rule-based part of speech taggers, but nobody thought of applying machine learning techniques to be able to parse a sentence and assign tag to each token of the sentence. I hope you guys are all familiar with what part of speech tagging is, right? So basically it means that my name is Keshav. So here you basically tag each word with its part of speech. So my is a pronoun, name is a noun, is an auxiliary verb, Keshav is again a noun. So there have been various approaches to parts of speech tagging. One has been the rule-based. The second, which was very successful, but was hidden Markov model, and then people followed it up with slight variations of Markov models, like maximum entropy Markov models. There were certain variations to that as well. Then some people applied SVM, and lately people have applied perceptrons and neural networks to this as well. Once you have done part of speech tagging, you actually do sentence parsing. What sentence parsing basically is that once you have tagged each word with its part of speech, you basically determine the relationship between each of those words. In the sense ki my name is Keshav. So here there is a relationship between name and Keshav. So name is a noun, Keshav is a noun, but there is a relationship like whose name it is. A more appropriate example is let's say who stole the pen. So here steal is a verb, pen is an object, and there is a relationship between steal and the pen. So this relationship between the verb and the object is something that you parse out of the dependency parsing. There are various algorithms to sort of building a parse tree, in the sense that there is a root out of which the main subject will form the root, and what is the verb or the action that the subject took, and the action, what object was affected by the action, and things like that. So that parse tree is something that becomes very important to extract the meaning out of a sentence. Okay, so there are again two main approaches to this. Lately neural networks have been used, but probabilistic context-free grammar parsing has been in use, and I think people who would have sort of tweaked with compilers or would have taken compiler courses would understand or would recall that they had to use shift reduce parsers to build parse trees out of the tokenized program input. Once you have done this, there is mostly the last bit is named entity recognition, or in short NER. When you are given a sentence, named entity recognitions are basically tokens of a sentence which are named entities, like name of a person or name of a location or timestamp or things like that. This is the most important bit as of now in natural language understanding, because if somebody says so let's say we are trying to develop a chatbot for bus booking, and somebody says I'm looking to go from Hyderabad to Bangalore. Now Hyderabad and Bangalore are named entities here. Each of those entities are locations, and the way you would actually end up arriving at its meaning that these are named entity locations is you would first do the part of speech tagging, wherein you'll get Hyderabad and Bangalore are nouns, and then you'll do the parsing with which you'll actually come up with a dependency relation between Hyderabad and Bangalore, and then you will identify Hyderabad as a named location entity, which is the source, and Bangalore as the named location entity, which is the destination. I actually wanted to get into details of some of the pause tagging algorithms that have been in use. Interestingly, any pause tagging algorithm that you use, even the dumbest one, in the sense that there are a few words which are ambiguous in meaning, in the sense that let's say SAW, saw could be either past tense of see, or it could be the axe kind of a thing with which you actually cut a wood. You just take any word, take the most appropriate part of speech of that word, in the sense that saw almost always occurs as a verb, right? It very rarely occurs as a noun. So you take every word, you assign its most used part of speech, and the pause tagging algorithm that you'll end up building will have a more than 90% accuracy even then. So even the dumbest algorithm actually has more than 90% accuracy. The bit between 90% and 100% is what becomes tricky, and the sentences that make it trickier are again one, the words which are ambiguous in nature, and two, the sentences which are longer and are connected with conjunctives like and, or, and things like that. Okay, so when you have ambiguous words in your sentence, or when you have conjunctives between parts of sentences, you actually need to learn sequences to assign tags with each token or the word in a sentence. Naturally, all the sequence learning, machine learning models would be suitable candidates for this. The most used ones are hidden Markov models and maximum entropy models. The hidden Markov model, what they do is So hidden Markov model basically tries to learn the probability that you have seen some part of the sentence. Now you are going to assign the next token a particular part of speech. What is the part that you have seen? Based on that, in the sense that if you always know that noun follows noun, verb is followed by noun, right? So if you have seen a noun uh, just now, the next token is either going to be a noun that completes this noun, in the sense that let's say if somebody has a first name and last name, Keshav Pravasi did this, so it could either be a noun or it could either be a verb, right? So based on what you have seen so far, you assign a probability of the next token becoming a particular part of speech. The maximum entropy model actually goes a step further. What it does is it sort of effectively computes all the candidate complete part of speech tag sequences, and then sort of calculates that sequence tag which has the maximum probability, and it throws in all the features of a particular token as well, in the sense whether it's capitalized or whether it occurs after a noun or a verb, or whether it's you know, whether it's a noun or not, and things like that. SVM has been applied, but not to you know, in certain scenarios actually SVM works quite well, especially when your sentences are not grammatically correct. So SVM actually works mostly on lexical features and the word features. So it actually works quite well even if your sentence is not grammatically correct. Recently again, deep learning techniques have been applied. So I think it's been a while, almost 2 weeks I think, that Google released a syntax net. So they have their own part of speech tagger, which is quite interesting. Yet to play around with this. But each of these basically achieve a baseline accuracy around 96 to 97%, and each of these is actually suited for a different purpose, something that I'll come on to later as well. In the sense that there isn't any one machine learning algorithm that works for every purpose, and you have to make your decision of what algorithm to use based on what data you have and what kind of data you have. So that was the part about natural language understanding, which is a part of natural language processing. So just to recall, there are 3 key parts to that. One is the normalization, you clean and normalize the input sentence. Second is the part of speech tagging, and the third is parsing that tagged sequence into a dependency tree or a relationship tree. You will only be able to extract meanings out of semantic meanings out of those sentences when you have actually achieved a fairly accurate dependency tree, which is possible only. So and the accuracy of the dependency tree that you parse is very much dependent on how accurate your part of speech tagging is. So it becomes very important that your parse tagging is really good, and that is why I wanted to cover this in detail. Okay, so and this is a different topic that I wanted to talk about, text search. It's not going to be that much technical. So I think all of you would be familiar with text search, in the sense that you input a few words, and then you have a corpus of documents, and you come up with the document that should be matching this sequence of words that is input as a query. There are various approaches to text search. One is the bag of words model, in the sense that you take in all the words that you just got in the query. You run through all your documents and see which of these documents actually have the words that the user query has. And you return all those documents, ranking them in the order how many words occur in which document. A more advanced implementation of the same bag of words is the vector space model, where you actually take into account the vector similarity between the query and the document, in the sense that each word actually of the entire dictionary of the corpus becomes a vector. So each document is represented by a vector. The query itself will be represented by a vector, and you determine the similarity between each document's vector versus the query's vector. the third is something that has come up really recently, like for the last 10 years. So it does not just do a word matching, no matter how advanced. It also tries to, understand the nature of the query, in the sense that whether it's a question, whether it's a query for recommendation, uh, and presents you with results that match your query the most. In the sense that it is not just about the query, but understanding the intent of the query as well. Whether the intent is to get an answer in the sense to get some information out of that query, or whether the intent is to get some kind of recommendation, or whether the intent is to get you to a particular website and things like that. So there are basically two broad things that we do in semantic search. One is the question answer systems, which are important for us because we are building a chatbot, and the other is topic based searches. Topic based searches basically mean that you are interested in a particular domain. Okay, like let's say you are looking for the best restaurant that serves chettinad chicken, which is a kind of South Indian chicken preparation. So here your topic is very narrow, like you are interested in food items. So there are actually knowledge bases that you can build out of a certain domain, which would be able to give you the best search results for that particular domain. This is something that is very important for us as well, in the sense that we actually are building chatbots for all the various domains, like for food ordering, or for travel, or for events or movie ticketing and movie suggestions. So it becomes very important for us to build knowledge bases on each of these topics or domains, and be able to get you the best recommendations for that particular topic. The way we do this is we build knowledge graphs of certain topics. For example, let's say food is a topic. Okay, to be able to understand all the food items on not just the word level, but to be able to understand it semantically, you would want to understand what is the cuisine, whether it's a spicy or a non-spicy food, whether it's a healthy food or a fast food, whether it is suited for breakfast or lunch or for a quick snack. So these are various attributes of a food that basically capture the semantic content of that food item. Okay, so when you, let's say, if somebody says ki I'm interested in chicken butter masala, there is a graph database that has as one of its nodes chicken butter masala with various attributes, like it is non-veg, it is spicy, and there are certain nodes which are not actually food items, but they actually capture certain categories, like Punjabi is the cuisine, spicy is the type of, like, spicy or non-spicy. So you basically, when you're trying to do a search, you do not do just a text search, but when you get chicken butter masala, you actually try to find out rest of the food items that you can reach via this node. And in what manner do you reach that food item becomes important. In the sense that, like, if you build a graph database out of these food items and their various, topical categories like cuisine, or the occasion type like breakfast meal or snack, you would actually get a lot of similar items after 2 hops. Like after 2 degrees of separation in a graph, you'll get very similar food items. And if you complete a cycle, in the sense that chicken butter masala is a Punjabi dish, just disregard the directions of the arrows. So if it were an uncyclic graph, a chicken butter masala is a Punjabi dish, chicken tikka masala is also a Punjabi dish, chicken tikka masala is spicy, and spicy relates to chicken butter masala. So if you complete a cyclical graph with so many number of hops that has 2 food items in it, there is a very good chance that those 2 food items are similar. Okay, so that is how you actually build a knowledge graph based search engine. It could also very well suggest you rest of the Punjabi dishes, or rest of the Punjabi dishes that goes as a side dish with chicken butter masala and things like that. Same could be applied to movies as well, in the sense that all the movies have a lot of attributes, like who were the actors in it, who was the director, who was the music producer, what is the genre, what is the certification rating, in the sense that whether it is PG-13 or G-rated and things like that. What is the rating, what is the IMDb rating for this movie and things like that. And based on that, you could build a very rich graph database out of movies, which you can search. So yeah, that sort of completes my presentation for the NLP and search systems. I also wanted to sort of briefly touch upon when you are actually going to design ML systems, in the sense that I believe you guys, a lot of you guys would be just getting started on, you know, doing something out of machine learning algorithms that you keep hearing about. Okay, so when you get a problem, like you have a huge data set and you have a problem to solve out of this data set, how do you decide what algorithm to go for? In the sense that, should I use SVM, or should I use a linear regression, or should I use KNNs, or should I use some kind of clustering algorithm, or should I use neural networks? This decision basically is based off a lot of different considerations. One of the very important considerations is that you should actually be trying to find the distribution of that data. In the sense that, what is the probabilistic distribution of that data? What I mean from this is that, let's say you have gotten a huge data set where each data point is a 10 member vector. Okay, so you basically try to find for each of those vector points what is the distribution. In the sense that, if you fix rest of the vector points, what is the distribution in this just one vector point, versus what is the joint distribution across all these vectors and things like that. So the moment you find the distribution, you will actually see that a lot of algorithms are suited for each of those distributions. In the sense that, if it's a Gaussian distribution, you would probably be good with linear regression, versus if it's a linear distribution, you would be good with applying SVMs, and so on. So there is actually no one size fits them all algorithm. There is no one pill for all cure here. You should actually know two things very well when you are starting out. One, the general class of machine learning algorithms, and two, what are the data distributions over which these machine learning algorithms are effective. The other thing, so once, let's say you have made this decision, okay, in any machine learning system that you're designing, there would be various steps where you would be actually putting this through a lot of different models. So for us, you do pause tagging with a different machine learning model, and you do dependency parsing with a different machine learning model, right? You do the normalization that occurs as the first step with a different model. If you do all these things in a sequence, there is a very good chance that the errors from, so any machine learning algorithm basically will just give you a probability of occurrence of this particular data point in a certain category or with a certain value. And there is an error associated with it. So if you do all these things sequentially, your errors will propagate from one step to the next. Okay, so so you should always be looking to design stateful systems rather than sequential systems when you're designing a holistic machine learning system. To pick an example, one of the problems that we deal with by designing a machine learning system is that, let's say you are given a sentence like, I want to go. Okay, I want to go. What domain does it relate to? Does it relate to bus booking? Does it relate to cab booking? Does it relate to going for a movie? Or take a very descriptive sentence like, I want to go from Hyderabad to Bangalore. Then you are pretty sure that it is either bus booking or flight booking. So you are actually trying to pinpoint the domain of that sentence. The way you would do this, you would either search in an n-gram model. If that doesn't give you any answer, in the sense that any of the n-grams in that sentence is not there in your n-gram list for any domain, you basically pass it on to your advanced NLP systems, which will actually do the dependency parsing and see what is the main verb in that. Often the main verb will basically tell you what domain it should be related to. But you do not do the normalization then and there. You do the normalization only when you do the spell check and the sentence cleaning only when rest of the NLP system fails to give you any domain, in the sense that there are high chances that the user actually typed the correct sentence. So no need to actually pass it through your normalization engine, because that engine might end up transforming the sentence to a different some of the words in that sentence to different words altogether, with which your whole NLP system will actually go down. So you run your NLP without correcting the sentence. If you get domains good enough, you go to the NLG unit that will respond. If you don't, only then you pass it through the normalization system, which again gives you the corrected sentence to the NLP, and that again runs the domain identification algorithm. So never do things in a sequence if you can. If you can get rid of some of the steps for some of the cases, you should always design a stateful model to achieve your overall goal. Yeah, that's it. Thanks a lot, Vivek and Mabel, for having me here.
Thanks, Keshav. Keshav has gracious of you that you're not there and still you go for the session. Keshav needs to leave early, so we'll have Q&A for Keshav right away. The remaining Q&A we'll complete together with the other two speakers. So, any questions?
Hi Keshav, thanks a lot here. In NLU slide, you mentioned as an example for this thing you mentioned Dahu, right?
Right.
So, suppose there is a statement wherein the statement mentioned there was Dahu is my favorite band. Now, if it is Dahu is my favorite, and there's no context of band there,
right?
And if that Da is a typo for Doctor DR,
right?
So there are two different contexts here. So how
of course there are. So again, so that is why I was actually talking about stateful systems, right? So you let both of them propagate, and then one of them will actually do not result into anything meaningful, and the other will. So
you let both the trees continue, and then
exactly.
At one point one will stop, the other will.
Yes.
Thanks.
Hi. You mentioned about the knowledge graph database that you built, right? So for building that also, are you kind of looking at like co-occurrence of like spicy and chicken butter masala to build that, or is it more domain?
Yeah, sure. So we are actually looking at all that, and so the kind of eventual recommendation that we do is based on the content-based recommendation. A similar kind of algorithms that Netflix follows for movie recommendation, or Pandora follows for music recommendation. In the sense that for each of those food items, there is a vector that characterizes what are its characteristics, spicy and other things, right? All the attributes, and another item. If you get a good similarity between these two vector representations, then those two are similar.
Next up, we have Chandrakant from Arya.ai.
Hi, good evening everybody. I just want to know, before starting, says how many of you are active machine learning user? If you could just raise your hand for my clarity. Active machine learning user? Okay. Yeah, but like you, in your day-to-day job activity, or coding activity, use machine learning algorithms. Okay. And any active deep learning user, in the sense working deep learning? Okay. So I did not prepare any presentation. I will just go through some standard tutorial or things available on the internet to give you a brief idea about what deep learning is. So I will be presenting my talk. I will be talking about basics of CNN and RNN, only the first basics, and then the Vivek from Ishnab Shauber, he will be covering more about when to use this algorithm, etc., etc. So he will be taking more from the usability point or from the architecture point. And then it will be basics of CNN, how it works, then RNN, then I'll be, as based upon time, I'll be give a quick walkthrough to a research paper, which is about action recognition in the videos, which uses both CNN and RNN, and a live demo, like we can upload a video and we can see how it's working, etc. So if you want to, anybody who are interested in deep learning and learning, this is a good resource, which is a Stanford course. When I started with this. So on the left hand side, this is a basic three-layer neural network, which is a multi-layer perceptron, which was pretty much in use in like few years ago. And then on the similar concept, they started working with another neural networks. So the most famous ones are convolution neural network and the recurrent neural network. So what are convolution neural network? In conventional machine learning algorithm, we do feature extraction and feature definition from on our own. For example, in the case of let's say you want to do object classification or anything in SVM, so you would do histogram oriented features or any shift related features, and you give those features to SVM or logistic regression, and then you get the output. So instead of doing this feature extraction on our own, we use CNN, the convolution layer specifically, so that does the feature extraction part. So the basic requirement is we must have sufficient amount of data, otherwise it will simply mug up all the data as it has huge number of parameters. So that's the first requirement, and it's pretty basic that we must have sufficient data. And how does they extract the features? So if you, any of you might have played with histogram of oriented features, etc., edge-based features, what they do is they really convolve the image with some filter, etc., and they extract the key points. Key points could be any robust feature, could be corner, etc., or edge points, etc. So same thing is conceptually this convolution layers are doing. So given an RGB image as an input, so let's consider this as a 32 cross 32 cross 3 and an RGB image. So it has 3 channels. We can take 3 channels, 1 channel, whichever you want. And then the next layer, convolution filter. So let's take it as first convolution layer. And let's say size is m cross n cross some z. So this is again, so you are transforming 3 channel to a particular number of channels when you are convolving this image to with the convolution filter. Now how to decide on what kind of filters we should proceed with, etc., etc. So in the beginning, it also depends on image size too. So if your image size is pretty huge, you should you can start with the large size filter, like say 11 cross 11 or like 22 cross 1. But generally we start with basic 5 cross 5 or 7 cross 1 filter. And also if the image size is pretty large, we downscale the image size to avoid the time computational complexity and the parameter size. And those filters, they convolve over the image. So when I said like the convolution layer is m cross n cross particular p. So p are the number of the filters. So you are converting 3 channel image and into a p channel image, and this each p channel of it is, so you can see it in 3. So this is interacting within each of this 3D cube. You are getting a layer, which is each layer is extracting a particular feature. So just to show you how the feature calculation is done. So let's say this was your input image. And so it's a 3 channel image, and so your filter is like as the input is 3 channel, your convolution filter should also be 3 channel, and then you define the number of filters you want to use. This is one filter. So each of these filters will extract a particular type of features. What kind of features it extracts, I'll show you. So you can comprehend it easily that this is your m cross n cross 3, the 3 channel image. So this 3 channel filter, it is convolving over the each RGB channel of the image, and then it is like doing the multiplication, addition, and converting it to a single value. And the last one is the bias, a single bias for each filter. So now just to visualize the filter. So now this can give you pretty much idea. These are the example filters learned by, this is a famous AlexNet, example of AlexNet, who won the competition of ImageNet, if you are aware of. So he uses this on his network. So these are the features which are extracted, and it's the visualization of the features. So we can see that it is, I mean, this kind of filter, you see, this is a kind of trying to find out the diagonal features. If this is kind of convolution of in the diagonal side, this is on the other diagonal side, etc., etc. So this you could see. So it is trying to find out the filter which were you doing manually. It is trying to learn the same filter on its own. And then after the convolution, we have fully connected layer. So fully connected layer does the inference part of it. So convolution layer on an intuitive layer level, convolution layer, they extract the features, and the fully connected layer, it tries to comprehend what class in it, what the task you want to do, whether it is object classification. So it try to infer the objects in it. And then we have finally we put a softmax layer or something to categorize or to find out the probability of which class is occurring. So that's the basic architecture. You give the input, you have convolution layer which does the feature extraction, then you have fully connected layer which tries to find out the class in it, and then you have finally softmax layer which find out the probability of which class is occurring. It's called probability. Now I'll move on to the recurrent neural path. So in convolution neural network, or what we have seen is like the single image itself is an independent entity. Like, so if we are doing a human, like we want to find out human in the images, in single image there will be a human. So you give 10 images, in say 8 it is there, other 2 is not there, but the images are independent of each other. What you give first image, the second image must or not necessarily has any relation with it. What if your data is temporal in nature? So we have, for this we generally use recurrent neural network which takes care of this temporal relation. So let's take the example of action recognition in the video or doing any analysis in temporal data. So if you want to do action recognition, then here there was a sequential relation between the frames. You would want to capture the relation between each frame, like what was happening in the first frame and what its relation with the second frame. You want to give sequential input. What you learn in first frame, give it to the second frame, and give it to the frame consecutively to have an additive knowledge of the underlying data. So this is a basic recurrent neural network, and it has loop in it, and how this loop opens up. So this is basically, for example, let's take we took that data with the of t span. So you give the x0 frame, and then it learns something, and it passes its knowledge to other one, and then it goes on in the same manner. So in recurrent neural network, so basically there is a cell unit. There are different type of cells which are used based on their structure. So most popular cell unit which is used in computer vision is LSTM, long short-term memory. And why long short-term memory are used? Generally, the problem with recurrent neural network was overfitting. They used to overfit a lot. So this LSTM unit, they have a certain mechanism in which you can force them to tell that which frames to remember and which frames to forget, and this helps a lot in reducing the overfitting. So now is it little visible? So now I wanted to show you an example where CNN and RN both are used together in a single framework. So in RNN, when you are giving input, the inputs are in terms of features. So for example, if you are giving an image, you have to convert it into a certain feature formation, and then you have to give it. So what generally we does is, we train a convolution neural network on these images, and then we take feature from certain fully connected layer, because it has already learned the inference, the relationship between the images. So it gives a very good representation of the image data set. And then we use those images as a feature which we give directly input to the recurrent neural network. So for example, if you had the video, you convert each frame into a feature using the convolution neural network, and then you feed that input feature vector into LSTM. So for example, if this is the first frame, you convert it into visual feature using CNN, and then you give it as an input to LSTM. Just for information, this is like one LSTM layer, this vertical one, and then there's another stacked over it. You can stack as many layers as you want based on how much input data you have and how much learning you want to do. Generally, we are done with 2 to 3 layers. We don't go deeper. And then over that, this is the prediction which you want. So this information is passed in the first layer itself, and then you can pass into the second level of learning. So this is the first level of learning, and this is the second level of learning, and in this manner it goes on. As output, you can take output from each unit, each LSTM unit, or you can take output in the final. What I meant by each output unit, we have already trained a CNN on these kind of images, and we get the features, etc. the features have good knowledge of what is in the image. So for example, if you are doing a video recognition, you might want to find out what the class is there in each and every image. So in the first image you find the guy is playing volleyball. You second image you find it tennis, and then you might do so you find the class in each and every image, and then you might do an aggregation model. You see like, okay, which class is more frequent in the videos. There could be a video which is like many games in the background, and the one is prominent. So you could build any kind of model. You may want your this classifier to find out only one class, then you can take output only from the last layer. So you can make your model based, and this is totally experimental that I'll show you later. So this is the use of CNN plus RNN. Now I'll show you a demo because I tried to implement a similar like same architecture on like UCF data set you might have heard of, University of Central Florida, on 11 video classes data set. So just for the demo purpose, I tried to train on some certain 10 to 11 classes using the similar architecture. First I trained a CNN, then I took the features from the fully connected layer of the CNN, and then I trained an LSTM unit with 2 stacks and find out. So in the meantime, we'll just go through the video here. See. So this is just a horse riding video. No, I don't want sound. I mean, I just extracted the frame part of it, not the audio part of it. So what I trained on was they all were 3 to 4 second clips from the UCF dataset, and which was pretty downscaled version of it, so very noisy dataset. And just to test the robustness of my algorithm, I tried to experiment with some YouTube videos that how is it working. So what you see, all those noise coming in the frames, etc., all those text coming in the frames, they play as a role of noise, and they are good of testing. This will take some time because it will initiate a AWS machine on, I mean, a instance on the AWS, and then it will try to train the data. So in the meantime, I'll tell you what I did. So I have while training, I had very short videos, like say 10-second videos, etc., 300 frame maximum. On the YouTube ones, the videos are pretty long, and I have like 1,000 frames, etc. So what I did was, and in every frame there is not necessarily there's some content available. So I clubbed 5 frames or 10 frames or etc. I mean, I tried this model that out of first 5 frames, which class is coming up, the next 5 frame, which class is coming up. In this manner, I tried to make an aggregate model to find out the most prominent class in the video. Why I did this? Because I am trying to take output from each and every unit, and this is the part where like this classifier will give you certain output, no matter with what probability, it will try to give you some output. Even if there is nothing in the frame, it will show you, okay, there is horse in the frame or something, because it is a probabilistic classifier, and it will give probability, and you take the top probability out of it. So you will infer one class out of it anyway. So that's why I tried to club all this. So yeah, so the output, like it was related to horse riding. Anyway, like I tried 10 to 12 videos, so I was getting pretty decent accuracy, around 60 to 70% on YouTube videos, and on the UCF 11 video dataset, my accuracy was pretty good, like around 85 to 90%. It took me around 1 week to implement this and test all this on AWS machine. So similar thing you can also experiment with, like use a basic CNN framework. If you have, I mean, just to start with, you might be aware of NVIDIA Digits platform. So on this NVIDIA Digits platform, you don't have to code anything. You can just give your architecture, like how many convolution layer you want, what normalization scheme you want, etc., etc. You can just give text. There's a standard .protobuf for text file format. You can modify the layers in it, and you can just give that layer and the input data in it, and it will help you in visualizing, etc., everything. So you can start with NVIDIA Digits platform, and then later on you can start coding on your own. So for the coding purpose, I use TensorFlow and Keras. If you were aware of it, Keras will help you in very quick coding, and TensorFlow gives you pretty much flexibility in handling multiple GPUs on a single machine, not on cluster, but on single machines. Now, a similar example I would want to show. 1 second. 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 1 Now also like convolution neural network, they are also used to find information like a sequential information. For example, this is a paper which I am showing it to you, is a paper which is related to Google Street View recognition, how they had a program in the project in which they took all the images from the Google Street View and they wanted to find out the house numbers. They wanted to do the recognition on the house numbers captured from the Google Street View images. For example, this is a 700. So they use totally convolution neural network to do a sequence recognition, but in a single image. So here, so we have, I mean the image, the numbers, the house numbers could vary. They restrict it to 6 characters or 5 characters. Now how it will work? So let's go with the model. And just to tell you the complexity of the this project, the house numbers could be written in any format, any color, in any manner, the way you want the design. Last. Okay, this is the part I wanted to explain. So as I told you, like they developed a convolution neural network which they called as deep max out network, and so there was CNN part and the fully connected part, and instead of connecting single softmax, when we do object classification, we do a single softmax layer to find out the distribution over the classes. Here what they did is, first they put a softmax layer, let's say layer, to find out for that how many number of digits are there in the particular image. So the first one gives you the probability of number of characters in the image, and then the rest. So they had, I told you, like for five characters. So for these 5 characters, so they put 6 softmax layers. First one gives you the number of characters in the image, and the rest 5 will give you the probability of each character from 0 to 9, and then some strings. So there's some example which they showed you. So there's a 128 cross 128 cross 3 image, and then it was 175, the house number. And how they did one? The calculation part. Just reading. So you see, so there were 5 classifiers related to the number of characters. So the probability of getting 1 and all these digits, it's showing. So this is the character which is predicting with maximum probability, and they just took the log of the probability, and they made a probabilistic classifier because occurring of first number was independent of second number, and then so on. Like if it is 175 or 176, they are independent of each other. So they, instead of they took the log of the probability and they just added, and they find out which distribution has the maximum probability, and they predicted that one. So in this manner, we can even use convolution neural network for sequence prediction. And if you have some temporal data, for example, the video or object recognition, action recognition in the video, you can use our recurrent neural network. And the use of the CNN plus RNN combination, some of you might have gone through the Facebook video where they ask like, what is in the image, and it answers cat or some animal in the image. They use the same kind of architecture. They, instead of, for example, in video recognition, I was giving output as the action in the video. So I was giving like volleyball, horse riding, etc. Instead of a single action, the word, you can even give a complete sentence, and then you can let the recurrent neural network learn the video, what is in the video, and then ask it to predict the next 5 or 7 or whichever sentences you wanted. The way then it predicts the complete description of that video. So in similar manner, you can have again in which part of the image what objects are located. Those all architecture works on the project. They work on the similar architecture. I also like prepared a sample code, but I don't think it's as like most of you are not actively using deep learning to show it. It was just with the TensorFlow. So I mean, if you want to start with, there is a good character recognition competition on Kaggle just for experimentation. Instead of using SVM or etc., you can try any deep learning based model. It's pretty simple, and some of the things which will be useful when you are doing it. So it gives you trained data, and That's all you have, like train and validation data. So you train on it and then you validate on it and you get some accuracy. While submitting your network, so you, on the validation data, you have, okay, I'm getting 97 or 98% accuracy, that's good enough. So after that, utilize the complete data, because now you're sure that your model is not overfitting and it is working pretty good, because you're getting a good amount of accuracy and validation data. Combine both the data and then retrain the algorithm on it with a reduced learning rate for some more epochs. Because you know your model is robust. Now you can have like more data to retrain it again, and that will push the accuracy like the last few percent, like 0.5 or 0.6, and that matters a lot. So mostly more than the architecture, how you make your data, how you train your data matters a lot. In most of the competition, etc., what they do is the data set is not good enough to learn everything. So what they do, they manually distort the data set, they rotate the images, etc., to make it robust to different kind of variations. All these are pretty important when you do a real-time application, because what you get in the test data is not actually the representation of the population you will be working on or for real-time application. So when you start with the basic data, you are not getting the accuracy, do some transformation, rotate the image by, like flip the image, do 10, 20-degree rotation, and then increase the data set. Instead of simply replicating the data. Many guys, what they do is they just replicate the data to make it more, like to increase the numbers. So, I mean, that's one of the important part. I guess I covered the basics of CNN, RNN, and its application. For question and answer, as she said, we will be taking it afterwards together. So, that's the information. Thank you, guys.
Is deeper the better? Let's find out from Vivek from Snapshot.
So, hello everyone. Am I audible at the back? So I'll be talking about is deeper the better, but before that I'll like to set a context for you. Like in deep learning we say deep learning, but what's so deep about it? As in the depth of the network that we use. Like recently if you follow, in 2012 the depth of the network was 8 layers. 2014 probably 16, 19, GoogleNet 22 layers. But how deep is it sufficient that you go and you get better performance? There's a trade-off always. So the latest thing that has beat the human performance in a classification task went deep to 152 layers. That was ResNet by Microsoft Research. So I'll be talking about in what cases going deeper is better and in what cases deeper is not better. So probably I'll be mainly talking around ImageNet and the classification task in computer vision to give you an idea about the system's performance and pretty much about the competition and how people benchmark their algorithms. So this is again a sample distribution of the training images used in ImageNet. So a brief idea about ImageNet, what it consists of is it has 1.2 million images, 10,000 classes, sorry, 1,000 classes, and the task is to given an image and perform the classification. Original dataset consists of a lot of images, but people used to benchmark on this dataset. The original dataset contains around 22,000 classes and somewhere in billion images. So, yeah, as like spoken, like the CNNs, the deep neural networks that you perform try to understand the features. They don't, you don't have a manual feature engineering task for your classification task compared to the previous methods that we have seen before 2012. People used to manually hand engineer the shift features or hog features, something like that. So, yeah, in CNNs what they do is that it's automatically engineered. And if you want to go get an intuitive understanding, let's say a classic example of LXNet. So the initial layers, as mentioned by Chandrasekhar. So the initial layers try to learn high-level features, something like edges, vertical edge, horizontal edge, a tilted edge at probably some angle theta, color blobs. The initial layers in the convolution layers learn that. The later layers try to club those features and form complex structures. Probably if you visualize the filters at the lower layers, you'll be again considering ImageNet classes, you'll be probably able to see eyes of animals given in the data set, and which has a lot of dogs and cats in them. You'll be probably able to see tire of a car or a bus, and some high level structures like that, apart from the edges that you see in the initial layers. Now, I'll give you a brief overview about the architectures. So, in AlexNet, if you read the paper and you see the initial layers, they have a filter of size 11 cross 11. That is very huge filter. So, from a practical understanding and from what researchers have also felt, it's advisable not to use huge filters. The disadvantages that you get for using huge filters is that it will shrink down the image size or the input size by a huge amount. So that's not what you want, because as the title suggested, the deeper the better. Again, it has its pros and cons. Yeah. Yeah, it's advisable to use lower filter sizes. So in AlexNet, they used 11 cross 11. Now they realized that was a mistake. So in 2013, when Zeeler and Ferguson published their ZFNet, they used a filter size which was pretty small. I'm not sure about the size, but it was smaller than 11 cross 11. And in 2014, two famous architectures, my personal favorite, VGG and GoogleNet. So the thing about VGG is they brought entire uniformity to the entire network. So it was around all 3 cross 3 convolution filters only, nothing more, nothing less. And GoogleNet, they did something in optimization and engineering side. Like in GoogleNet, they had fewer number of parameters. So it was kind of easy to computationally calculate things. And the number of parameters, again, less. And they did a module called Inception module that was introduced by GoogleNet. So, and yeah, finally back in December 2015, there was ResNet. That was 152 deep layered network. So ResNet has its own problems, like if you try to deploy ResNet, it will take a huge computation resources from you. So you'll probably need a good infrastructure, hardware infrastructure, or else it will take a lot of time. So yeah, as I mentioned, like if you see these features, this is from this layers. So these are edges and blobs. This is again a structure, high level structure combining these features, and this is the final template, kind of templates that you get when you train a deep network, and finally you can perform the classification task. But again, as I mentioned, there is always a trade-off that happens for, in terms of performance and a computational cost. So yeah, now I'll dive deeper into like when it's good to use a deeper net and when it's not. First thing, you have a number of classes. If you want to train your network on, let's say, 100 classes or maybe 200 classes also, the more deeper network, it depends on how you have your intra-class and inter-class variations, or else it's like sometime over engineering to use a deeper feature, deeper net. The amount of data available to you for each training class. Let's say you want to classify, for example, flower and animals. For flower and animals, they are two simple classes and kind of very distinct apart. So going with a deeper net, you can definitely achieve accuracy probably around 99.5%. But what's wrong with 99? It's at times it plays a crucial role. Suppose you build a self-driving car and you need a classification thing. At that time, 99.9 is required and 99.5 probably won't work. You might drive over someone, and that's not a good thing. So amount of data, the larger, if you have very huge data, it's advisable go for deep. You'll get good performance. But again, there is one huge problem about deep nets. It has a tendency to overfit. They very easily overfit, and you have various techniques to avoid overfitting. But still, if you have less amount of data and you have probably more number of classes, it will easily overfit. So don't go for that thing. Intra-class variations, if you have huge variations within your class itself, then go for a deeper net, but you should have a huge amount of data. If you don't have good amount of data, try to go for a shallow one, because the system's performance would be really bad. And interclass variation, if you have the hardware resources, go for it, or else don't. And that was very quick. So probably everyone might agree with me now. Is deeper the better, given that you have more number of classes, you have good intra-class and interclass variations. Probably everyone agrees with me, or not.
You told to use Keras and other libraries for our practice. Are they used in development purpose also?
I mean, when you want to do POC, use Keras. When you want to do real-time production code, you don't use Keras because they are developed over TensorFlow and Theano, and they add an extra layers. And in your production mode, you are not using all the features of Keras, so they add extra complexity to it. So in our company RA.ai, we do POCs mostly using Keras, or in sometimes if you want to do quick testing, we use some other tools which are built by us only on our own platform. But in production mode, we use TensorFlow and Theano and Caffe. These three we have restricted. So for I prepared ES model. So to get the features from the images, I use pre-trained LXNet because it is pretty good. As he said, it is trained on 1 million images, and the results we have already developed results. So use standard LXNet weights. I mean, I trained it on my own on the same data set. And I stored the weights on my for use of LSTM. So you train a CNN separately. You get the weights, okay, and then you use those weights to give to encode the image into feature for LSTM, and then I mean LSTM will give you a final output. I don't remember the size of the weights, like when you add up and when all those are saved, what size they occupy. I don't remember exactly the size. Like I can give you an idea if you can drop me a mail, or I can, yeah, sure, because I don't remember. I did it long back just to explore recurrent neural networks, and they could be used in some use cases like surveillance in ATMs or etc. etc. So yes, so one was this model, but the LXNet which was already available then was not good enough. So I retrained again the trained LXNet. So I had some LXNet with 70% accuracy. The weights were available on the, I guess,
yeah, model. They have the weights.
You added one more layer, again trained it on more data.
So LXNet with like some 70 to 80% accuracy, model was already available. So I did not start with scratch. I took that model with the same architecture, and I iterated the cycle for 1, 2, 3 more times just to get a good.
Those images, you ran it on all those million images?
Not million images, not on the million images, like some set of those images, not on million images.
As a continuation to this question, if you do something new today, how will you test it?
Test in the sense accuracy of the system?
Yeah,
or so for this, we have standard data set from UCF, which I was mentioning, University of Central Florida. So you can start with like, video sets of only 11 classes to develop a miniature model, or with less classes, so you won't have much difficulty in training, etc. Then they have 101 classes data set. Scale of the architecture, 10 on 101 video classes, and then there is one more with like more than 1,000 classes.
And
1 million.
What's your test data?
Huh?
What's your test data?
So
Same data set, you basically divide it into test and train.
Okay, now again, in continuing this question, if I have a mobile weight, can I test it?
As
a string?
I mean, it will take a lot of net and battery of the mobile. Yes, so what
Not possible.
Not for mobile.
I thought if you had better.
No, I'm not working on mobile platform yet. That how to integrate it the mobile.
Mobile was just used as an input.
But
yeah, that can be done.
But if you have a direct streaming of a camera, it's saved on the server and it does on the server. That's possible.
Yeah.
That's the pretty much.
Deploying the entire thing on the phone would take time, sir. Would take some time.
Yes, as you mentioned, pretty much. Even if you want to do it on the weights, the files, they occupy a good amount of space. It's not easy to.
It occupies around 200 MB. So I just wanted to know your model does it occupy less space or?
I don't.
If you want to do it on a mobile, you have to download 200 MB of your training model, and then that can.
So
if you download also, again the competition are so heavy. You cannot perform on your phone yet.
The ideal way is always push these videos onto the server, do the calculation there, and get the output. Nobody will do on this mobile application. This is not feasible.
For a complete beginner, what would you recommend? For a complete beginner to the field, how would you recommend? So there was systematically learning.
This is the course which I was mentioning. So go through this course, which is like CS231. It is the mother and father everything of deep learning and static. Yeah. So it has explained
pretty much in detail about all the basic stuff to get you started in computer vision, especially because this course was mainly focused on convolutional neural networks for visual recognition. And probably the professors who teach this course are kind of the creators of the ImageNet competitions.
That's good. That's pretty good.
Okay, my question is related to the usage of your platform as such. Like how to build the applications on top of your platform, and like what are the skill set required to build the apps on top of your platform?
You are talking about the complexity of the problem I'm facing, or how to use it from the utility purpose?
Let's say I want to develop one business app on the top of your platform. Okay, how do I go about it? And what kind of support you provide, and what kind of skill set are needed to embed your platform into the other business applications?
So, as of now in our platform, whatever application we have, we provide you the standard input format. So, you basically they are all API calls. So, the standard input format for even for the data set you want, there is a standard data set format, either in the JSON file or in the for the video purpose you upload your data on some EC2 machine. It requires good amount of technical skill because you have to. We'll be just giving you the output. So you give us the input and we'll give you the output. Whatever the application you want to build, that you have to code on your own. For example, let's say this the video recognition example itself. So you want to deploy it for surveillance thing. You give us the video and we'll be doing this action recognition and we'll give you final output of the recognition. You can build any application out of it. You can prepare, like you can give write a code and it takes the dump timely from the camera and then upload it to the EC2 and the server, whichever platform you want to upload, we will access from there. We will give you the output. So we will be processing, doing the main algorithm part of it, taking the input, giving you the output. Rest all the utility thing has to be built by the user itself.
And just to continuation of that question, like if we have to like build a text system, a voice recognition system, which will give the speech input to you, and then how you will recognize that what is the context of that speech? Do you need a training set of data from us, or what?
So as of now, we haven't started working on the speech part particularly. In the text case, whatever the we have tools or the application for test based, you can user can give his own training data set. We'll be training on it, and then he'll giving you output. For example, in the first talk that guy was talking about, Keshav was talking about named entity recognition, etc. So we have a model which does this named entity recognition and which use or build a question answer website over it. So for example, you give a data set, you want you can train the system on our data set, it will do the named entity recognition. So for example, you want to scan a resume of a person, or let's say you want to do a take the resume thing. You give the details. Something will pop on the screen and will ask user to write his details. The system, the algorithm will automatically take all the information which are required. For example, his name, age, where he was working, what was his salary, etc., etc. It will try to take all the information. If it is not able to take, it will give you an out like pop over in some way that okay, I wasn't able to get your name. Could you please write it again? And he writes the name, and then this way it can automatically captures all the information. And that could be saved in a database and you have it automatically. So that's the one use of named entity recognition. Same way it could be done for hotel booking, etc., etc. Like you just write your location, okay, I'm there, I want a hotel, and then it can give you a good database, and then it will ask you. That's like an interactive one. Okay, what amenities do you want, etc. So those all NLP tools we also have on our platform. You can use it. The thing is, the application part has to be built by you. Whether you have to use for like booking purpose, or you have to use it for some resume scanning or some other information gathering, etc. on your website. So that front end part has to be designed by the user. The platform part will enable with the data, uploading the data, etc. So you don't have to worry about the backend part where the server is how much space would I be needing, etc., etc. Everything will be taken care of by the server. The only thing is the inputs and output are fixed, and then you can build anything which comes in on your mind based on that application or that algorithm.
So we can sign up for right, or there's a special requirement for that.
So as of now, like we are in like up and down mode because we are doing changes continuously. So our backend is changing a lot. I mean, more frequently than it shouldn't be. So we are taking limited, giving limited access based on use cases. For example, in some cases we have matured applications, so we have keeping them constant as of now. So if you subscribe and you give your use case, etc., etc., and it suits or like the algorithm for it or tool for it is constant, you will provide it access.
Okay, thank you.
How do you, narrow it down to the, say it's clothing apparel? I mean, how do you make sure it stays in that clothing apparel? How does it not, go something else? There's something that looks more closely to what the clothing apparel is.
Something. So initially, when someone uses it, there's an instructions. Currently, it focuses only on the specific vertical. And again, it's not a B2C product, so the user directly don't interact with us. So probably there will be a business company who will be integrating us. So they have specific instructions for the user. You take certain items, and again we have a filtering mechanism in place. So it filters out the items on the user query. Because ultimately the product will be in the real world, so you never know what would be the input.
Say I get a clothing apparel in Bangalore. What's the probability that I get the same thing again in Bangalore? Maybe how do you make sure it stays in this location itself? Like if it doesn't redirect to some other location, some probably Hyderabad or maybe Chennai.
Sorry, I didn't get you. As in, yeah, the results that you get would be on online products. You can easily buy them if you are interested in buying.
And do you have a payment gateway?
It won't be ours. Okay. It will be the users. We are not a direct consumer facing company.
So like Flipkart can integrate your
Yeah.
product
Yeah. So payment, the user traffic would be yours. So user will be using your app only.
Okay, thank you guys.
Thanks everyone. We have some snacks, some burgers and some soft drinks for everyone. We just opened this session for networking right now. Thank you.